So we're going to start talking a little bit more about, a little bit like nuclear physics, but really, I would say on the surface, but with a lot more depth than you could study on your own. Okay, these are our really last 2 lessons of the year. Okay, we have 2 lessons left in the whole year. We have 1 more double period with the lab. We're going to work on the DC motor during the double period. And then we have 1 day of review. And then your test is next Thursday. So keep track of your dates for the next couple weeks.
Are you excited that we're almost over?
I can't wait to get rid of you, Joe. Can't wait. There you go. I know, but that kind of a question is tough for me to answer, right, Joe? Without me feeling bad. I'm so excited to not be teaching. That's kind of, you know. No, I love teaching, but I do also enjoy the summer a lot. I enjoy both. So we're going to talk about some properties that occur in the nucleus and how the nucleus is a little bit different than what we're seeing around us on like a macro scale. We'll talk specifically about what's called the strong force, and then talk about stability, what gives and takes away stability in the nucleus. So first, the word we're going to start with is nucleon. And a nucleon is any part that is in the nucleus. So the major parts that we talk about are neutrons and protons. Where are the electrons? They're outside of the nucleus. And we saw that with the Rutherford gold foil experiment, that there was empty space, right? So the nucleus must have been this concentrated mass at the center. Turns out the nucleus is insanely dense, like insanely dense. That's why structures can't really go through them. Even though there's a lot of empty space, they're still quite massive in atom, if you think about it. The density of the nucleus is extremely large. Now, the rest of it, though, being empty space, makes the entire atom not as dense. So, for example, if I take a piece of copper metal and I measure the density of it, I'm measuring not the density of each nucleus of the copper, I'm measuring the density of each atom. And the density of the atom is a really dense nucleus with a really open space in the rest of the atom, giving you an average density of what we write down as the density of copper. Okay? Now,
it's like the atom bomb. You split the nucleus.
We're getting there. Don't ruin it. That's next class, actually.
Spoiler alert.
We're going to talk about fission and fusion next time.
No
Yeah, that is it. So symbols-wise, we should know this has to do with the atomic number. The atomic number is what, really? The number of
Electrons?
possibly, but always protons. Electrons you can lose again, right? So the atomic number at the bottom is always the number of protons. So hydrogen is atomic number 1. There's 1 proton. Okay? Helium is atomic number 2. There are 2 protons. Now, the atomic mass is the sum of your protons and your neutrons. So how many neutrons are there based on these numbers? 14. 13 protons, 14 neutrons, yielding 27 as a mass number. So again, the mass number is the sum of those 2 particles. It's the total number of nucleons, really. Okay, the total number of nucleons. Neutron number is never really written down, right? Okay, but we could say A equals, in this case, Z plus N. And that's just logical. The mass number is the number of protons plus the number of neutrons, Z plus N. Z plus N. All right, let's go to the next slide. There's not much more on the slide at all. So on the next slide, we talk for a little bit about amount of protons versus neutrons. For the most part, you'll see that a lot of elements have a similar number of neutrons to protons. Similar number. And in that last case, there were 14 neutrons and 13 protons. But when you have a variable amount of neutrons in an element, it creates what's called an isotope. Last year, chemistry talked about isotopes. So what is one element that is very much, or that occurs in many different forms of isotopes? Remember from chemistry? There's certain elements have different isotopes. Uranium for sure, because uranium, you know, is like U-235, U-238, and there's usually an average of those. Carbon also. Carbon and uranium are the 2 they're always talked about because they vary in isotope, because they vary the number of neutrons. Now, the mass number that's actually written down on the periodic table is not one of those isotopes. So for example, uranium could have a mass number of 238, or uranium could have a mass number of 235. This one has, 235. This one has 3 more neutrons than the other one does. Okay, the actual, what's the atomic number of uranium? I don't know personally, it's not a quiz.
It's like
Something
86
you look it up?
plus. It's like, it has to be.
It's
like-
high up, I know, it's radioactive. What's the atomic number for uranium? Which one is it? Just Google it real quick, come on.
My bets are on 111 or 86.
Uranium? Atomic number? Somebody? Bueller? Bueller? Thank you, Isabel. 92.
Split the difference.
Okay, so what's happening? Keep that up, Shannon. Keep that page up. What does it take? What does it say is atomic mass in the top left? So atomic mass. Atomic mass 238 point. All right, I want the decimals. So go ahead. 238.02891. Okay, so that's the atomic mass listed on the periodic table for uranium. But uranium cannot have that atomic mass. Okay, uranium's atomic mass is 235 or 238. So what is this number actually? What is this number? Anybody know? Chris?
Is it like the number plus the mass of the electrons?
Huh? I like the idea though, because the electrons weigh very little, right? Electrons have very, very, very low mass. What do you think this number might represent? Okay, let's start with this. Okay. Not nice. So these, again, if an element can have more than one mass, they're all isotopes. So U-235, U-238 are both isotopes. Isotope simply means that the element can have multiple different masses. So if the element cannot have more than one mass, it doesn't have isotopes. It has only one element. But if an element can have several different masses based on the number of neutrons, it can have different isotopes. This is not an isotope. It's something else. Here, I'll give you a hint. Look up carbons for us, Shannon. Look up carbons. Because uranium's not as obvious. Carbon might make more sense. What's the atomic mass of carbon? Carbon, what number? Is carbon 8 or 6?
6.
6? Okay. Now, carbon can have, can you look up the carbon isotopes also, Shannon? Thank you. Tell me the isotopes for carbon. What are the possibilities? That's the actual mass, but what are the carbon isotopes? I mean, 12 is obviously one of them. Is it increase in neutrons or decrease?
It says 13, 12, 14, 11, 15, 18, 10, 9.
Wow. 8, 10, 9, 15, 16. Okay. So I ran out of room. So all of these numbers that you're seeing here, take a look real quick. All of these numbers are different masses of carbon based on if it has more neutrons than it should. The regular one for carbon is 6 protons and 6 neutrons. That's the most abundant form of carbon on Earth. So look at this number. It is closest to this number. Do you notice that? Because this is the most abundant form of carbon on Earth. So what might this be actually? Come on. Math skills. Use your math skills. An average. Well done. It is an average. If you took all of the carbon that existed and you looked at the proportion of how much there was of C612 versus C613 and C614, there is very little of C613 and 14 and 8 and 10 and 9 and 15 and 16 that occurs. The majority of carbon that's naturally occurring is C612. So if you took the average of all these particles that are occurring, the average turns out to be a mass of around 12, showing that that's the most abundant of the isotopes. So for uranium, the same thing. U-238 is the most abundant of uranium that exists. The average is quite close to U-238. Where do we go?
This uranium has so many more neutrons than no. Yeah.
It does.
The protons.
As you go up on the periodic table, the number of neutrons is not going to be the same as protons. It's going to change. Part of it has to do with nuclear stability. Give me like maybe 2 slides or so, and I'll talk more about that. Okay, I'm gonna get to that, I promise. But just give me a minute or so. What else for this? Isotopes, given elements. Okay, let's go to this next about density. Okay, so first, nuclei. Nuclei are considered to be spheres. They're not perfect spheres. Good.
As good as you can get.
All the sensors.
All the sensors are in here.
Good. That's what matters the most. In the workers, you know?
I'm gonna just cross off this result.
Yeah, that's fine. And if you know, I mean, I guess you can't figure out which motors are broken, right? At this point.
No, but
I
I
can
know
figure out next year. I'll do
1
that.
in 6 is.
So the density.
Hydrogen, this number is what, right? Does it have one?
I'm pretty sure hydrogen is just a proton, correct? I don't think hydrogen has. Does it have a neutron in it? In its nucleus? Or is hydrogen simply a proton by itself? I remember from last year in chemistry. Hydrogen, does it have a proton? Does it have a neutron? Does it have an electron even in orbit? Does hydrogen have an electron in orbit?
Yeah.
Just a proton.
Has 1 electron and 1 proton? Is that what it
Yeah.
is? It should be because we calculated the electrostatic force between the proton and the electron
Yeah, yeah.
earlier this year.
Hydrogen bomb.
But does it have a neutron? Is what we're saying.
It does.
I think so.
What's the atomic mass?
The internet says doesn't.
Just look up the atomic mass of hydrogen. If it says 1, then it's just a proton. It says 1 for the
Yeah.
atomic mass, then it's just a proton. If the atomic mass was 2, it'd be a proton and a
I
neutron.
guess you don't need it if there's just 1 electron and 1 proton.
What is the what do neutrons do?
Give me a minute and I'll get to the next slide. I promise I'll get into that. It's all about nuclear stability. The neutrons and protons together create what's called the strong force. But you're just ruining the surprise. You know, that's all it's happening. I'm kidding. But just give me a minute. Let me get to it. So the density of the nucleus is a function of its size and its mass. It is generally a sphere. Okay, the nucleus can be approximated as a sphere. It's not perfectly spherical, just like the Earth is not perfectly spherical. The volume of a nucleus in general is generally proportional to the number of nucleons. So that means that the density is pretty constant as a result. So most nuclei, doesn't matter if they get bigger or smaller, have the same density. So if I have a nucleus that's pretty small and there's 2 protons and 2 neutrons, say helium, and then I get boron, which I think is 5. I gotta memorize my numbers better. Okay, so now I've got another atom here. So I think boron is 5.
I think it's
The number of protons and neutrons combined, right? The nucleons double, so the volume actually will also double. The mass and the volume are proportional when it comes to increasing nuclei. So as the mass goes up, the volume goes up proportionally. Therefore, the density is a constant. Again, as it gets larger, it gets bigger as well in mass and in volume at the same exact rate, which makes the density of general nuclei for any atom, the density of the nuclei is the same. Yes, it gets more massive, but it also gets more volume. Here, give you an idea, right? Give you an idea. The density of the nucleus is on the order of 2.3 times 10 to the 17 kilograms per cubic meter. This is, let's see, where is it? Ready? Here's your number. This is 230 trillion times more dense than water. So think about water. Water's a good, a good point of reference, right? Things sink or float in water. If things are less dense than water, like wood, it floats. But metal sinks. A nucleus, again, is 230 trillion times more dense than water. Trillion, not million, not billion, but trillion. So the density of a nucleus is extremely, extremely high. Okay, for a nucleus. Okay, now, having such a high density does not necessarily, though, give it a lot of gravitational pull. Remember, gravity is G(m1)(m2) over r squared, right? M is very, 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 very small. R is very small also. R is very small as well. But M is extremely small. Now, if you go back to your notes from electric force, we calculated gravity in the nucleus. We literally found out the gravitational pull between a proton and an electron for the hydrogen atom. Then we calculated the electrostatic pull between them as well. The electrostatic pull was far, far, far greater than gravitational. So the gravitational pull doesn't really matter. Okay, it doesn't really matter between the nucleus and the electron on the outside. Now, within the nucleus, though, what kind of charges do you have in the nucleus? Neutrons or in the nucleus, protons. Neutrons are neutral, protons are positive. So the nucleus is an abundance of positive charge. What do positive charges do to each other? Like charges repel. So why isn't the nucleus splitting apart? If you have a lot of protons, right? Between every proton in the nucleus, you have an electric repulsive force. An electric repulsive force between the actual protons. And that actual force, believe it or not, is enough to cause the protons to move away at speeds of, we're talking on the order of 2.3 times 10 to the 25 meters per second squared. Accelerations, I should say. Absurd amount of acceleration. Absurd. Yet, somehow, the protons are not separating. The nucleus is not exploding. There's a reason for this. And that's where this next theory of stability comes into play. That's where the concept here of what's called the nuclear, or AKA strong force. Okay, the strong force, another word for it is the nuclear force, is responsible for holding the nucleus together. The strong force is a force of attraction, believe it or not, between nucleons, even if they're both protons, even if they're both neutrons, even neutrons and protons. This is a different force. It is not a polarity-based force. It is a proximity-based force. So what I mean is this. If I had a proton here and a neutron here, there would be no nuclear or strong force because they're too far apart. But when you squish protons and neutrons close enough, you suddenly get this attractive, almost like a cohesive force between the protons and the neutrons and the neutrons and the neutrons and the protons and the protons. And that force of attraction is what is combating the repulsive electric force between the protons. Two protons by themselves, they want to shoot apart, but the strong force is holding them together. It has to be on very, very, very small distances. We're talking on this order. Okay, we're talking way below nano. Nano is 10 to the negative 9. Okay, this is on the order of 10 to the negative 15 meters. So a very, 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 very small distance between them. Now, for heavy nuclei, the more neutrons, the better. Because neutrons don't give you any repulsive force. Neutrons only give you the strong force. Protons, the strong force holds them together. The electric force pushes them apart. So if I have a very, very large element with a lot of protons, right, like this, let's just say this is all it is, and let's say hypothetically there's only 2 neutrons here. This would be an unstable nucleus. If you have far more protons than neutrons, the nucleus becomes unstable, and as a result, you undergo radioactive decay. Radioactive decay. Now, the way to stabilize a nucleus is for it to have more neutrons. Because again, the neutrons provide more of the strong force. The protons provide strong force, but the protons also feel a repulsive force, which is the electric force. So the protons naturally want to push away from each other. These push away. These push away. These push away, right? We see this? They're literally pushing away from each other. But because the neutrons are there, well, there's attraction here. There's attraction here. There's attraction here. There's attraction here. Attraction here. See what I'm doing with the blue arrows? I'm drawing all the attractive lines. So the neutrons create more of a nuclear force than the protons do, because the protons also create that repulsive force. So for a nucleus to be stable at high atomic numbers, you want the number of neutrons, which is N, to be greater than the number of protons, which is Z on our earlier reference form. So the number of neutrons, you want to be greater than the number of protons for large nuclei, or heavy nuclei. Now, uranium does have an abundance of neutrons, but not enough, which is why its isotope, or its isotopes, are radioactive. Uranium is 238. Its atomic number, we said, is 95 or 92. So 238 minus 92 is more neutrons than you have protons, for sure. For sure. The problem is this. What kind of a scale does this work on? Very small scales. So uranium, being a huge atom, has big distances in the nucleus, much bigger than the actual nucleus of a hydrogen atom. So as a result, that nucleus is a lot bigger. And this force works best at really small distances. So unfortunately, even though uranium has an abundance of neutrons, more neutrons than protons, it is still not a stable element. Okay, so this is to create more stability lines, but it's not saying that because you have more neutrons than protons, it's automatically going to be considered a stable atomic number, or a stable atomic element. Yeah.
Uranium is on its way to be stable, right? Isn't uranium like?
What do you mean?
Doesn't it get stable eventually somehow?
Well, the whole idea of half-life of radioactive decay is that eventually it never will be stable. But over time it would, yeah.
Does it become another element?
It's so when it's giving off radiation, it's giving off in the form of energy. So it is changing. It's absolutely changing. We're going to talk more about nuclear fission and fusion. So when you see uranium split into other parts, it's physically changing its elemental form. Like a fission bomb, for example. I just don't want to give away that's the whole next lesson. That's why. A fission bomb itself is the splitting of a nucleus into two separate things. Traditionally, I think uranium splits to barium and krypton, those two elements. So it's physically changing its shape. That's an example of a fission bomb. But the actual element of uranium, like pure uranium over time, loses its radioactive nature. Every half-life, it loses half of its radioactive mass. The mass is still there. It's not like it's going away, disappearing, but its radioactivity is going down.
But what's the half-life? Like a couple thousand?
Yeah, I forget the half-life of it. I mean, carbon dating is used for this.
Yeah.
Half-life dating, carbon dating is what they're using. They're using, what element of carbon is it that's radioactive that they use for carbon dating? Is it C14? Chemistry? Really? I think it's carbon 14. I'm pretty sure I remember in high school. Carbon 14 was the one that was radioactive. So they use carbon 14 for carbon dating to actually see how long something has been in existence. Because carbon is like the building block of life, whether you realize that or not. I don't know if you ever talked about that in chemistry class. Without carbon, nothing could exist really. I mean, there are a couple elements that are like that as well. Oxygen being one of them, hydrogen being another, helium another. But carbon is like a fundamental building block to all things. So carbon dating is used for anything. For bones, for fossils, for plant life. Anything that lived at some point in time had carbon in it. So carbon dating is used to see how old certain things are when they're excavated, when they're discovered. Yeah? I know your question was a little bit different, but the idea of uranium being a certain mass is not going to change. Now, a fission bomb, it actually splits in different parts. Actually, it's not bad. Questions? I wanted to leave a little time at the end. First, questions on your project. Your project is coming up soon. The deadline is due pretty soon. Any general questions you want to ask? Any issues you've had? Any things of concern? There's no write-up for this. Okay, there is no write-up for this, right? I'm correct? I didn't put that on there? I think in the past I used to do a write-up for one thing. Trying to think of anything else end of the year matters. The 19th is our field trip for those who signed up. Don't forget, it's at noon on the 19th. No, we're going to that physics show.
Oh, really?
I didn't do it with you guys last year. I did it 2 years ago.
Mm.
I don't know why I didn't do it last year.
When's the egg drop date?
What's the date for it? I have it on here. You have it? 21st? Is that when it's due or is that the date?